Welcome back to our last example for this lecture. Wow, that's crazy. 3 examples. The last lecture was so many of them. But yes, this is our last example for this lecture, and this is hopefully not going to take too much time. Again, this is 2 parts, and for this one we have to find an orthogonal matrix P such that P tap diagonalizes A, and then we have to verify that it gives it in the proper diagonal form. And so it's like what we did in the diagonalization lecture, but as you can see, instead of the inverse P, or in this case it was the inverse S, we have an inverse P, which is in turn our transpose, which is just going to be awesome because we can easily find the transpose. So let's get started on this example. So the first one, we are given a 2 by 2 matrix that are all ones. Again, as I mentioned in the last video, these are all going to be symmetrical matrices, which is the cool thing about it because we can do so much things about it. So as always, when it comes to diagonalization, first thing that we must always do is take the determinant set equal to 0, aka our characteristic equation. And so we'll have 1 minus lambda quantity squared minus 1. And that is going to be giving you lambda squared plus 1 minus 2 lambda minus 1, or the ones cancel out, factor lambda, lambda times lambda minus 2, giving us our eigenvalues equaling to 0 and 2. And we have 2 eigenvalues, so they're going to each have 1 eigenvector. So for the eigenvector or eigenvalue of 0, we're just going to get the same matrix. So I'm not going to bother to write that down. So that means our eigenvector will be 1, negative 1. And then for our lambda is equal to 2, we will get 1 minus 2, negative 1, 1, 1, negative 1. So that means the eigenvector will be just 1, 1. And so because we are looking for an orthogonal matrix, even though we were to find our eigenvalue, we have to, if you recall in the lecture, the process of doing this, once we find our eigenvectors, we have to convert it into a unit vector. And so what this ends up being for the lambda is equal to 0, we will have a unit vector being, it will be 1 plus 1 squared plus 1 squared, which is 2. Take the square root of that, and it'll be root 2. So our unit vector will be root 2 over 2. And if you do not remember how to do this, I will link a video that should be showing up in the top right corner right now. And for our eigenvalue is equal to 2, we are going to have the same thing, it's just there's not going to be a negative. And so combining all of this will give us a orthogonal matrix P that is going to be, we're going to have our eigenvalue 0 being the first one, so this would be root, that's a bad one, so it would be root 2 over 2, and then negative root 2 over 2, and then the other column would just be root 2 over 2, root 2 over 2. Cool. So what that means is that our transpose will be root 2 over 2, root 2 over 2, negative root 2 over 2, and then root 2 over 2. And that's our P. And then when we multiply them, we will get PT times A times P, and this will give us the transpose root 2 over 2, root 2 over 2, negative root 2 over 2, then root 2 over 2, and then we multiply A times P, we will get 0, 0, root 2, root 2, and so our answer, our diagonal answer, is going to give us 0, 0, 0, 2, which is the proper diagonalization form. So yeah, now let's go ahead and do the next example. So the next example, it is, is going to be a 3x3 matrix, so it's a little bit longer, but let's not waste too much time. And so this one, as always, find the characteristic equation. So our characteristic equation will be -2 minus lambda, 2, 4, 2, -2 minus lambda, 4, 4, 4, 4 minus lambda. And again, we can't do anything special to make our life simpler, so we're going to have to do this the typical way. And so what we end up getting is -2 minus lambda multiplied by -2 minus lambda times 4 minus lambda minus 2, and this would be 2 times 4 minus lambda minus 16, and then I cannot fit this, so this would be plus 4, and this would be 16 minus 2 times 4 minus lambda, right? No. This would be, hold up, 4 times 8 will be 8 minus 4 times -2 minus lambda. And again, this is all going to be equal to 0. So to simplify all of this, this will be equal to -2 minus lambda times lambda squared. I messed up. Right here, it has to be, because I did not do the subtraction. Okay. So move this a little bit to the right. So this would be, okay, so this is minus 16. So it'll be lambda squared minus 2 lambda minus 24, and then this would be minus 2 times -2 lambda minus 8. Yeah, and this would be plus 4 times 8 minus 4 lambda plus 16. Simplify this even further. This becomes, we can factor out this. So this would be -2 minus lambda multiplied by lambda minus 4 times lambda minus 6. So it'd be plus 4 lambda plus 16 plus 16 lambda plus 48. No, not 48, 64. And then simplifying this, we get 20 lambda plus 80. And then we factor out a 20, so this would be 20 times lambda plus 4. And then, yep, bring this down. So it'll be -2 minus lambda times lambda minus 6 times lambda plus 4. I realize this is supposed to be a plus. And then this would be plus 20 lambda plus 4. You can factor out the lambda plus 4, giving us lambda plus 4 times, we will have negative lambda squared plus 4 lambda, and this will be 12, 4, 20, 32. So this part will be negative lambda minus 4 times lambda minus 8. So our eigenvalues will be lambda is equal to -4, -4, and 8. So we can see that the -4 has a multiplicity of 2. So we're going to go ahead and get started with the lambda is equal to 8 case, as this will make, or since that one has only one eigenvector. So when the lambda is equal to 8, we'll have, so this will be -10 to 4 2, negative 10, 4, 4, 4, negative 4. And so our eigenvector will be 1, and then have this be 1, so this has to be 2. So we'll have negative 10 plus 2 plus 8, and then we have what I believe it'll be 1 or 2 minus 10, so it'll be negative 8 plus 8, okay, and then this one will be 4 plus 4 minus 8, okay. So this one works. And now for our lambda is equal to negative 4? Yeah. Oh, actually, before I move forward, let's convert this into a unit vector. So this would be root 6 over 6, root 6 over 6, and then this will be root 6 over 3. So for our lambda is equal to negative 4 case, we know that it's a multiplicity of 2, so let's just hope that the geometric multiplicity is also equal to 2, so we will have negative 2 plus 4, so this would be 2, 2, 4, 4, 4, 4, 2, 2, and then 4 plus 4 is 8. And we can see here that the first row is the same as the second row, and it's also double of the third row, so that means it has a rank of 1. So that means the nullity is equal to 2, which is great, which is what our multiplicity is. So we can still continue with the diagonalization. So that means the eigenvectors will be equal to 2 of them. First one being, I think I'll rather do negative 1, 1. That'll be the first one. Then the second one will be 3, negative 1, 1. And so that is our eigenvectors. And so now we have to turn this into a unit vector. However, we want to have an orthogonal matrix, P. So that means we have to make sure that this set of eigenvectors is an orthonormal set. So we have to do the Gram-Schmidt process. The first step is, the first one is equal to the usual vector, so negative 1, 1. So we can easily just convert this into a unit vector. So this would be negative root 3 over 3, negative root 3 over 3, and then root 3 over 3. And so our second one, remember, we have to use the Gram-Schmidt process, so it is the vector, the second one, and then subtract the dot product between the second and the first, so this will give us negative 3 times the magnitude of the first, which would be just 3, and then multiplied by the first, so it'll be negative 1, and 1. So doing this will give us positive, so it's just subtracting. 3 minus 1 is 2, 1 minus 1 is negative 2, then 1 plus 1 minus 1 is 0. And then the unit vector will just pretty much be 4 plus 4 is 8, so it'll be 2 over 8, so root 8 over 4, negative root 8 over 4, and 0. And so we're going to just get this all together and have our orthogonal matrix P equal to root 6, 6, root 6, 6, then root 6, 3, and then this would be negative root 3 over 3, negative root 3 over 3, and then root 3 over 3. And then our last one will be root 8 over 4, negative root 8 over 4, and 0. And then to find the inverse, well, because this is already an orthogonal matrix, just find the transpose, so that will be root 6 over 6, and then 6 over, not 3 is 6. It's the other one that's root 3, or over 3. Negative root 3 over 3, negative root 3 over 3, and then root 3 over 3, which is 0, root 8 over 4, and then negative root 8 over 4. And there we have it. And so now when you multiply this out, p tap, you will get, as always, we don't do anything with the first one, so it's just pretty much copy and paste. And then the second one, when you multiply it out, you will get 4 root 6 over 3, 4 root 6 over 3, and then 8 root 6 over 3, and then 4 root 3 over 3, again 4 root 3 over 3, then negative 4 root 3 over 3, this would be negative 8, or root 8, and 0. And then when you multiply all that all out, you will get the diagonal matrix 8, negative 4, negative 4. And that is our answer. And that is it for this example. Thank you very much for watching. And I'll see you guys in our final lecture of this course.